Good morning, everybody. Good afternoon, everybody. Our group would like to present our capstone project, which is the modernization of Chalkboard through digitization and smart capabilities. Our team will consist of myself, Shoei Kawa. I am the project manager and the software engineer. Derek Lamb, who is the software lead. Iyad Zaidan, who is the hardware lead, and Andrea Torrell, who is going to be our hardware engineer. Through this presentation, we would like to talk about our project's motivation selection, the design requirements, the specification we went through, the system description, related theories, software, hardware, system design and testing, timeline and cost analysis, code conducts, and ethical considerations. So as you know, technology evolved over time. The classroom environment, teaching environment has changed. It started off as a simple chalk and chalkboard, then it became marker boards, and currently we are now in the iterations of using smart boards. The issues with these smart boards are that they're very expensive, very expensive compared to their traditional counterparts. So what became actually popular was the marker board conversion kits, where they would put some attachment right onto the marker boards, and then they will convert that into a smart board. The issues with these is that they often create silos where the use of the marker board and the use of the smart features are completely isolated. If you wanted to use a marker board, you would use a marker, but then if you wanted to use a smart feature, you would have to pick up a specialized pen and then use it right on the board. What's actually even more egregious is that if you're talking about converting chalkboards into smart boards, which are available, it completely renders the use board unusable as a chalkboard, because what would happen is they would put on a wallpaper-like material right onto the chalkboard. So what we want to do is we want to reimagine the chalkboard as a teaching tool by adapting smart capabilities that will enable educators around the world. So this is going to be done through two key factors. It's going to be done through digitization and smart capabilities. The digitization is picking up the image of the chalkboard. We're going to apply image processing on it and allow it for saving and sharing. The smart capabilities are going to be enabled through projectors, which are available around classrooms, all over the classrooms in our campus all over. And then we'll allow touch interactability of the PC right on the chalkboard. The impacts we hope to have is improved environmental impacts because of uses of trying to get people to use chalk more over the plastic markers, and also want to remove the headache of using markers. I'm sure there are cases like you've seen these before. Professors will bring in bundles of markers thinking like at least one of these should work, ending up none of them work and they have to run out and get another one. So we would try to completely remove that and make it a little bit easier to use. And also another advantage of this project is the chalk and chalkboards are readily available around the world.
So during our project session, we have considered like 3 topics: a dedicated chalkboard for smart capacity, a chalk I've add-on to a chalk, and an add-on device to a chalkboard. For a dedicated chalkboard with a smart capacity, it can have using a touch capacity, but it would be inconvenient at a high cost. For add-on to a chalk, it can be tracked accurately for the movement of the chalk. However, the image quality after the image processing will be very poor. And then with the add-on device on the chalkboard, it is quite effective to improve existing chalkboard. But however, the accuracy and the response time will be less. However, after we using the HP which is as the decision matrix, we find out that the add-on to the chalkboard is the best solution and to doing our project.
As Shao mentioned before, there are similar products in the market. This chart shows us some differences between those products and ours. As you can see, the most noticeable difference is the price. I know though there's at the engineering building we have a Google Jamboard. Imagine having one of those products in every classroom. It will be just extremely expensive. Next. And we conducted an interview with one of the philosophy professors at Manhattan College. Some of the things we discussed were the importance of connecting with students through handwriting. He also shared that after every class, he takes a picture of the board and sends it to his students. Most of the times, the boards he works with his students are unique. So based on that and some other researches, we came out with with that identification of the needs of our projects. That is as follows: use the regular chalk, easy to use board, tracks with computer, projects to screen, and it also has a fair price. Next. When it comes to design, we have four different categories. High image quality, which the goal is to use a camera that captures and picks up a clear image from the original. So low image distortion and low noise. The next one is easy to use experience. Besides being easy to use, we want to push out data fast to the computer and as well as receiving it fast. Third one is deployment, multiple data formats and easy to install. And the fourth one is affordability. Next. Here we have some marketing versus engineering requirements. As you can see, the left side of this slide translates to the right side, which means, for example, for number 3, for marketing requirements, we have image should be uploaded quickly. For engineering requirements, translate to should be able to capture image and upload it in less than 15 seconds. And that you can compare every one of those. Next.
Actually, you are muted.
Oh, sorry. All right, so real quick from the beginning, from the top. So for the camera is going to pick up the image. There's going to be attached to the board. It's going to pick up the image. We're going to do the image processing on a personal laptop that's going to be connected to it. The RF mesh is also going to be an attachment on the board, and we're going to have the touch interaction that's going to be replicated onto the personal laptop.
So in the software part, during the coding of the image processing, and one of the part of the image segments, we are trying to use reference a new algorithm, which is named as a Fantan algorithm, and it's related to the adaptive binary size method from Singapore, and this is based on the criteria of the maximum local contracts for the image analysis. And during this, it's calculate the local mean, the local minimum, the standard deviations for data to separate text from the background by small shifting primary local window. And to comparize the effective or illuminations, the dynamics of the standard deviation is calculated for a larger secondary local window. And then for the threshold value is calculated into the surface. The image that input is binarized into a black text and a white background. And here is how the threshold value, the overall equation about that. And here it is pseudocode, and you can see it is a try to input a size of primary local window, a larger secondary windows, and a minimum tile values. And after that, it will output a black-white image of the chalkboard. And for the left side, it is a definitions of the local windows.
Here we discuss the science and the theory of IR emitters and sensors. We know that, in the IR emitters, gallium arsenide and aluminum gallium arsenide are mainly used to reduce infrared light because it can emit light with longer wavelengths than normal light. Energy is released in the form of a photon through the p-n junctions. This is done through the energy gap, which is energy needed to move electrons from the valence band of the atom to its conduction band. And as you can see in the formula Eg equals Hf, we can adjust the energy gap to produce the wavelengths we need to generate infrared, near infrared light. IR receiver, these devices use a fresnel lens to collect infrared light from any angles that are then directed into the infrared filter that blocks any light other than infrared. The light collected heats up the piezoelectric to charge the IR sensors and becomes high. Otherwise, it remains low. The responsivity of the IR sensors depend on the signal output into the energy and detected active area.
And as for the functional decomposition for the image processing, and it's going to pick up the image from the camera through a USB, and the output is going to be the processed image. The functionality within it is it's going to go through multiple image processing. So one of the things the few things are going to go through, it's going to do the skew, which is the angle correction. It's going to clean the image by filtering out chalk dust residue, and it will do other visual enhancement. And this is going to be enabled by using the OpenCV library using C++. And again, the output will be displayed on the laptop.
As for the function decomposition of the IR touch, the IR mesh will detect when interference is happening on the board. This signal will get multiplexed and sent to the Arduino in this case. In order to do this, we are using a 4051 multiplexer that works with analog values. S0, S1, and S2 are selected inputs, also known as pins. Depending on the setup of each pin, we will have an independent output that based on the truth table, which with a low and high setup, will send Y0 to Z, which is the common output of the output signal. Next.
So as shown, this is a whole flowchart of how the image processing as code. First, it will capture the board and capture the image by camera. And as it is a raw image, it converts to a raw data. And after a image inversions, turn it to a grayscale. And after extracting the image components, a fixed window image is produced. And then we will go to the image segments. By using the algorithm, the Fang-Tang algorithm that I just mentioned in the previous slide, a binarized image will be produced. And however, if we have some noise, some salt and pepper noise, and we are trying to use a medium filter to reduce the noise. After the reduced noise, if we have the image projecting and storage in here. And here is our demonstrations of the whole software coding. And since this is a live, so it's trying to capture the board and it try to having an image processing. And here is a fully perfect, I think it's perfect, image results of the board.
Here's the development of the circuit. The emitters and the IR receivers are collinear positioned. So at this state, the IR receivers are always high at reading 5 volts. And so once the IR receivers are blocked from receiving any IR signal, the voltage will drop, indicating a low state. The voltage levels are then sent to independent pins, Y0 to Y7, as Andrea mentioned, of the multiplexer, and the selected inputs S0, S1, and S2 will change according to the states of the IR sensors to generate the output. Data is then sent to the Arduino in binary to display the coordinates within the mesh. Here's a demonstration video. So in the video, the individual is moving their finger within the mesh. This allows the sensors to change voltage levels. The coordinates are then displayed on the monitor to represent the location of where the surface is being touched.
For the iterations for the hardware, we started with the small scale testing to see the IR sensors and IR emitters are working within the design parameters. And then we created one hub, which is one set of IR sensors and one set of IR emitters, and then working with the multiplexer to see all the system is working. And then we created 2 hubs to allow us to create the x-axis and the y-axis touching sensing. For the software, we initially started with the image capturing and preparing of the image before it goes through the image processing algorithm. The image processing was first tested with the O2 method, and we ended up with having mixed results. And then we did further research. We came along with the Feng-Tang algorithm, and we had some better result. As for some of our unit testing, this was one of our most simplest and yet fundamentally important mistakes that we found, and then we found it through our testing. So this was in that initial phases. We were testing 8 emitters in parallel, supplied with 5 volts, 180 ohm resistor, and we had 8 sensors on the other side. Theoretically, everything was calculated properly. We ran it through PSpice, everything worked. However, when we did the testing, we found that the sensors it didn't have any potential difference that is being generated. The emitters actually did have 1.2 volt, but it had no currents going through those emitters. So we went back to the drawing board and started to do the calculations. The emitter required 20 milliamp, 1.2 volt, and then we calculated the voltage for the resistor and for each of those emitters. So it turned out that because of the series setup, there was a lot of current that was going through the resistor, and it was having 0.72 watts, while the resistor itself was rated for 0.25 watts. So we were worried about burning out the emitter or sensors, but we didn't even consider the possibility of burning out resistor because it was such a basic component. And it kind of put us in place and thinking like, okay, we can't make any assumptions. We need to make sure we check every one of the components. That was a big learning point from this testing. As for the go, no-go milestone work, the hardware, they were required to pick up a touch interaction of an area and send coordinates to a PC, which was demonstrated in the previous video. The software was to complete a console program that will conduct image processing, invert grayscale, noise reduction, segmentation, and use a camera from a frontal view of a chalkboard, which was also completed. And this is our project schedule for fall 2020. As you can see, all the blues that we have accomplished everything we were trying to achieve. This is the project schedule for winter 2020 and spring 2021. It's a little bit hard to see. So here's a little bit blown up. So things to consider for the hardware is we need to consider the power supply consideration, because if we were to expand this, the Arduino is not going to be able to provide all the power. So we'll have to consider a dedicated power supply. And we will also, like I said, we will be expanding, so it covers a little bit more of the board of the small board we have at hand. For the software, we're going to be actually incorporating the skew correction, because we would imagine the camera to be on the top and pointing down. So we'll be correcting that, and we'll also start integrating the graphical user interface to incorporate all these features.
For the cost analysis, this is based on the project itself. The estimated price, it came out to be $120.93. This is based on a 2x2 IR mesh, and we have the camera, chalkboard, and projector is already provided. If we want to expand and make a bigger IR mesh, we have to consider more components, so the price will vary. And also, if we want to make this as a product, we have to consider the camera expenses, and obviously, like as Sho said at the beginning, we know that chalkboards and projectors are pretty much in every classroom environment nowadays. Next.
We came across these few code standard constraints. One of them, IEEE 802.11 standard for wireless local networks, IEEE 1394 for high-speed serial bus, and IEEE 310 reference standard for electrical resistors.
We have the ethical considerations. According to the IEEE, we are consideration of the environmental impact. Obviously, we're choosing chalk over markets. We are trying to make this product affordable for everybody, so we treat everybody fairly. We improve the understanding of technology, its appropriate application, its potential consequences, and the last one, be honest and realistic in extending our claims or estimates based on our project.
And in conclusion, we have successfully reached our go criteria, which allows us to go on to the next semester to continue on for our final products and possibly make some improvements upon it. And some lessons learned we got through this project is nothing goes according to plan, but preparation is vital. And we have reaffirmed that engineering is about facing issues and problem solve and just figuring it out. Thank you. These will be our references, and that will be it for our presentation. Is there any questions?
Yeah, can I have a question?
Yes.
Yeah, it's a very interesting project. Yeah, and also that you mentioned a very good promising results. You said that your results that kind of better than the phone pound algorithm. So can you summarize that what's the improvement you have made so that you said that it will yield better results?
Oh, okay. Derek will speak on that, and I'll
Sure.
go back.
Sure. Can you go back to the flowchart? Yes. So the difference between the O2 method and the front-end algorithm is, as you can see, that is the matter of the original backbord, and because we not just simulate that just writing words in the blackboard. We also simulate that after the there's like erasing dust it is be left in the chalkboard, and after we try to use the O2 method, the O2 method will recognize that the dust will as a part of the background, and it will and cover the words and also cover dust. And then after using the front-end algorithm, because it is using the criteria for the illuminations, it will filter the dust part in the backboard and left the words in the and separate the words and the backboard, and which will give a better performance other than the O2 method.
So for that, okay. So are there any like reason that you select the input image when you process that the local window size is 17?
It is actually like the tested numbers that we tried, and as simulated, it is the best number that I have tried it, and that's the number how I chose for this coding.
Okay. So what are the denoising? You mentioned that you denoise the image. So what specifically you did?
Yes. So after like the binarized image, there will like some kind of salt and pepper noise. We would do this, and the best solutions to reduce the noise is the medium filter.
Oh, just use the medium filter.
Yes.
Okay. Yeah. Actually, there is some other algorithm that has better performance than just a general medium filter. Yeah. Okay. Yeah. Thank you.
Welcome.
Thank you. We'll follow up with you. We'll be very interested to hearing what you can any recommendation you can provide.
So, for example, when you reduce the noises for the medium filter, actually it's a very simple denoising algorithm. You can use some other denoising algorithm. Yeah. So, for example, ranked order mean that is better than the medium filter. So also there's some other denoise algorithm that is better if you want to know more. I can send you an email about that. Yeah.
Yes, we'll most definitely follow up with you. Thank you.
Yes, thank you, Dr. Wing.
You're welcome.
If there is no further question, that will be it from us. Dr. Sultan?
Great. Thanks to Tess, Andrea, and Ed. Thanks for the presentation. And just to sum up my group,